Welcome to this video on graph isomorphism, where we'll explore the fundamental concept and the algorithms used to determine if two graphs are essentially the same. Let's begin by defining what graph isomorphism means in the context of graph theory. Two graphs are isomorphic if there is a one-to-one correspondence between their vertices, meaning the connections, or edges, are conserved. Simply put, they are identical in structure, even if they look different visually. The key challenge is figuring out if two given graphs are isomorphic or non-isomorphic. To tackle this, we look at several inherent properties that must be preserved between isomorphic graphs. Isomorphic graphs must have the same number of vertices and edges. The degree sequence must be equal, meaning corresponding vertices have the same number of connections. They must also have the same number of connected components and identical cycle structure, including the number and length of cycles. Now let's delve into the algorithms used for determining graph isomorphism. The brute force approach involves several steps. First, check if the number of vertices and edges are equal. Next, compare the degree sequences. If those checks pass, you must generate all possible vertex mappings and check for edge preservation under each permutation. If no mapping preserves all edges, the graphs are not isomorphic. Graph isomorphism has significant applications. Let's start with its use in chemistry. In chemical graph theory, molecular structures are represented as graphs, where atoms are vertices and bonds are edges. This mathematical representation helps in studying molecular structure, isomerism, and chemical properties, as seen in an example like methane. Another chemical application involves reaction rate graphs, or kinetics. Graphs of concentration versus time show changes during a chemical reaction. The slope of these graphs gives reaction rate information, such as the straight line observed when plotting a first-order reaction. In thermodynamics, graphs illustrate relationships between variables like pressure, volume, and temperature. These visual aids are crucial for understanding concepts such as enthalpy, entropy, and phase changes. Graph isomorphism is also extensively applied in computer science. In pattern recognition and computer vision, objects are represented as graphs based on features like edges and corners. Graph isomorphism determines if two images contain the same object under varying conditions, such as recognizing the same face or car from different angles. For social network analysis, users are vertices, and relationships are edges. Graph isomorphism helps identify similar community structures across networks, which is useful for detecting duplicate accounts or fraudulent patterns. In compiler optimization, control flow graphs represent program flow. Isomorphism techniques help compilers detect identical subgraphs or repeated code patterns, enabling optimization for code reuse and performance improvements. In database and knowledge graph querying, graph isomorphism is vital for structural matching. It efficiently answers complex relationship-based queries in graph databases like Neo4j, such as finding similar connection paths in professional networks. Finally, let's look at some practice questions based on previous GATE exams. Considering the two graphs shown, we can see that the graph on the left has a cycle of length 3, specifically the path ADC. The graph on the right does not contain any cycles of length 3, indicating they are not isomorphic. For these two graphs, let's examine the degrees. In the left graph, vertices A, C, D, and F have a degree of 2, while B and E have a degree of 4. In the right graph, all vertices have a degree of 2. Since the degree sequences are different, these graphs are not isomorphic. This question is from GATE CSE 2012, testing the fundamentals of graph isomorphism. Thank you for watching this video on graph isomorphism.